Okay guys, I'm back. Hopefully this works a little better. We did an update, computer restart. All right, so yes, this is where we left off. Determine the length of the radius given the coordinates below, then determine the 6 primary trig ratios. So here we have a terminal arm. So when we are looking at angles in standard position on the Cartesian, they always start on the positive x-axis. So this is an angle that has an initial arm here. This is the initial arm of the angle, and an angle that has its terminal arm here. And this is a line that I will add back in after. And so the distance between those two lines can be measured as an angle theta, and we are interested in determining the length of the radius that is created by that terminal arm. So if this is the coordinate 5, 3, that 5 is the x value of this coordinate, which is the horizontal distance from the origin, and the 3 is the y value of the coordinate, which is the vertical distance from the origin. And that's where we can put this line in here, and we end up with this nice right angle triangle that we could then label and say that this is the vertical distance from the origin, which is 3, and this is the horizontal distance from the origin, which is 5. And if we wanted to know the value of r, we can use Pythagorean theorem and say that r squared is equal to 5 squared plus 3 squared. Or we could say r is equal to, under the square root, 5 squared plus 3 squared, which is 25 plus 9, which is 34. So r is equal to the square root of 34. And if we know that, we can write those primary trig ratios. So we would say that sine theta is equal to opposite over hypotenuse is equal to 3 over root 34. Cos theta is equal to 5 over root 34, so we have adjacent over hypotenuse. And then tan theta is equal to 3 over 5 is equal to 3 over 5, and we could use these to also write our reciprocal trig functions. So cosecant theta is going to equal root 34 over 3. Secant theta is going to equal root 34 over 5. And cotangent theta is going to equal 5 over 3. Okay, so that's that question, and now we can derive some general terms from that. So in general terms, if you are given a coordinate we would say that would fall on the circumference of a circle, we could determine the radius of that circle using this formula. The x value squared plus the y value squared all under the square root is going to be the radius of that circle. So that's one important takeaway from this. And we could also say that sine theta of the angle that is created between the initial arm and the terminal arm will always be the y value, right? So opposite, this is the y value, over the hypotenuse. The hypotenuse is the radius. So sine theta will be y over r. Cos theta will be adjacent, which is the x value over the radius, so x over r. And tan theta is opposite over adjacent, which is going to be y over x. So these are some general terms that we can use that can help us in other questions where we are just given a coordinate. So we're going to look at one here, and I'm going to put this information off to the side so we can use it. So determine the 6 trig ratios of an angle theta whose terminal arm passes through the point -3, 5. Then determine the value of theta in radians. Okay, so here we are going to, actually we're just going to work on the trig ratios right now, and the reason being is we need to use the cast rule to actually figure out the value of theta, and we haven't reviewed the cast rule yet, but we are going to tomorrow. So let's just focus on creating our 6 trig ratios for right now. So the first thing we need to do is figure out the value of the radius using this formula here. So r is going to be equal to, oh, we lost our second part of the formula, but that's okay, under the square root -3 squared plus 5 squared, and we actually just end up getting the same thing, which is root 34. And because that's root 34, but what has changed is our x and our y. In this case, our x is -3 and our y is 5. So now when we are going into our trig ratios, we could say that sine theta, so sine theta is going to be y over r. 5 over the square root of 34. And then cos theta is equal to x over r. Well, our x value is -3 and our r is root 34. And then tan theta is our y over x. There should be an equal sign in there. So we have y over x, which is 5 over -3. And then we could use that to figure out our reciprocal trig functions. Now, I suppose we could still work on finding, well, no, we'll come back to finding the angles after when we review our cast rules. So there we have sine theta, cos theta, tan theta, and I'm sure it's getting a little repetitive at this point. Cosecant theta is just going to be the square root of 34 over 5. Secant theta is going to be the square root of 34 over -3. And tan theta is going to be -3 over 5, okay? So I'm going to just leave this here for a second. This is actually from the homework questions. I didn't include them at the end, no. So this is a very, very similar question. I'm not going to do them right now for sake of time, but do choose, at least I would say choose 2 of them in total and do them for homework. There's not a lot of practice for necessarily what we're doing today because it's all review. Everything mostly that we're learning is review from grade 10, grade 11, so there's not a lot of stuff in the grade 12 textbook for primary trig ratios, Pythagorean theorem, things like that. So, but this is a good question that includes what we talked about today, and so do a couple of these, page 330, number 2. And the last thing we need to review before the end of this lesson is special triangles. So what we are going to do is convert the following degrees to radians, and maybe you would remember these special triangles. So these are some pretty special degrees. Maybe you remember that from grade 11. 30 degrees is a really important one, 60 degrees, and 45 degrees. And so what we are doing is we're doing away with degrees and we're dealing with radians from now moving forward. So we need to convert these degrees to radians. So again, we're going to multiply by pi over 180. And then we're going to simplify and say, okay, I can divide 30 by 30. 30 divided by 30 is just 1. I can also divide 180 by 30, and that's 6. So if I divide both top and bottom by 30, that becomes 1, and this becomes 6, which means that 30 degrees is the same as pi over 6 radians. I also want to convert 60 degrees by multiplying by pi over 180. So similarly, I can divide top and bottom by 60, or I can cross cancel out here. That becomes a 1, and that becomes a 3. And that means 60 degrees is equal to pi over 3 radians. And then to convert 45 degrees to radians, I'm going to multiply by pi over 180. And 45 can go into 184 times. It goes into 90 twice. So we end up with 1 over 4. That should be a 4, which means that 45 degrees is equivalent to pi over 4 radians. So these are going to be, and if you haven't already noticed, these denominators, 3, 6, and 4, are really important on our unit circle that we are kind of getting more familiar with. Is we do see these increments of 3s and 4s and 6s, and then of course we have the half up at the top. And so what we need to do is rewrite our special triangles now with radians, because that's how we will be using them for the duration of this course. So where we previously had our 30, 60, 90 triangle, we are not going to have a 30, 60, 90. We're going to have a pi over 6, and we're going to have a pi over 3, but the side lengths still stay the same. The ratio of the side lengths is still the same. So we still have that 1, 2, and root 3. How you remember this is up to you. You might find it helpful with radians is, well, a couple things. The pi is 180 degrees, right? We know that halfway around the circle used to be 180 degrees and now it's pi. So if we split pi into, or 180 degrees into 6 pieces, you're going to have less than if you only split it into 3 pieces. So the smaller angle is going to have the larger denominator. That might help you remember that this one's going to be the pi over 6, this one's going to be the pi over 3. The larger angle is going to have the larger denominator. This is only 180 split into 3 pieces, so the pieces are going to have more. more in them. Another thing that you might help you remember is that the root 3 is going to be across from the angle that has the denominator of 3. I don't know, that might be helpful for you. 1, 2, and root 3. Another thing that some people get confused that if the 2 goes here or here, and when that happens, I always just remind them that put the square root of 3 in your calculator, and you will see that you get a decimal that is less than 2. So if you're ever confused and you're like, well, I thought root 3 was the hypotenuse. Well, put root 3 in your calculator. It is not larger than 2, so that means it must go here. We always seem to remember the 1. On our other special triangle, which was previously our isosceles, our 45, 45, 90, we are now replacing that 45 degrees with pi over 4. And both of them are 45, so both of them are being replaced with pi over 4. And again, the side lengths stay the same. We have 1, we have 1, we have the square root of 2. The other thing is that, like, this is just Pythagorean theorem, right? So the hypotenuse, if we think about Pythagorean theorem, is c squared is equal to a squared plus b squared. And also c is equal to the square root of a squared plus b squared. Well, we have to double check that that's true. This is the hypotenuse, and if we square 1, we have 1 squared plus 1 squared, that's just 2 under the square root, so that works out here. And here, it works out to be the same here. When we square this, we have the hypotenuse, which is 2, which is 1 squared plus root 3 squared. It does end up equaling 2. You could double check in your calculator. The other one that sometimes is helpful is doing the reverse. Under the square root here, let's just say this would have to be the square root of 2 squared minus 1 squared, right? The longest side squared minus another side squared, that's 4 squared minus 1 squared is equal to 3 squared. So however you want to remember is up to you, but we do need to memorize these special triangles. We're going to use them moving forward, and we're going to use them with radians, not degrees. So this is our new version of our special triangles. So determine the exact value of theta in radians given that cos theta is equal to 1 over 2. So if we're given 1 over 2, we're like, okay, well, which one of our special triangles has both of these side lengths? And that's our formerly 30, 60, 90 triangle, and now our pi over 3, pi over 6, 90 triangle, or right angle triangle, pi over 2, I suppose we should call it. So we can quickly draw that triangle out, and that's our one that is not our isosceles triangle. I'm actually not going to draw it because that's not a nice version of it. So I'll use this here and quickly draw a triangle. So when we have that triangle, that special triangle, I'm going to turn it this way so that it looks like our previous screen. This is the larger angle, so this is where pi is split into less pieces. This is the smaller angle, so this is where pi is split into more pieces. This is my right angle, and this is my 1, 2, and my root 3. My other special triangle doesn't have a 1 and a 2. It has a 1 and a root 2, so I know that I'm dealing with this special triangle. So I want to know which of these two angles would result, in other words, what is the exact value of theta in radians, would result in a ratio that is adjacent over hypotenuse of 1 over 2. So which of these two angles has 1 adjacent to it? Well, that would be this angle here. Okay, this angle has 1 adjacent to it, and and 2 as the hypotenuse, as the longest side. So therefore, theta is equal to pi over 3, because 1 is adjacent to pi over 3 and 2 is the hypotenuse. Another thing you can do is double check your work. Now, if your calculator is not in radians, and it does sometimes throw people off if they convert their calculator to radians, but if you could put your calculator in radians, you could actually double check. You could say, okay, I want to check. Let's put cos pi over 3 into my calculator and see if I get back 0.5. Now, if your calculator is not in radians, this is where we will probably use that conversion the most, is I want to check the exact value of this. I'm given my angle in radians, but I want to know the exact value, and my calculator's in degrees. So you could formally remember that pi over 3 is 60. The other thing you can think about is pi is 180 degrees. When we have that unit circle, and we have halfway across, this is pi. Well, that used to just be, we'll put the comma on the other side, but it used to be 180 degrees, and now we're saying it's 180 degrees is pi radians. So we could, to convert this back to degrees, we can always just replace the pi symbol with 180 degrees. So this is the same as cos over 180 divided by 3, which is cos of 60 degrees, which we did know from this triangle. And you can put that in your calculator. I don't have a graphing calculator open, so I'm just going to leave it at that, and you guys can check in yours, but you would get back 0.5 in your calculator, so you know you've done the work correct. Okay, that's it for today. I'm going to post the video for you for homework. Go back and do these, and we will move on to some new stuff in tomorrow's lesson. Mostly for today, you're going to focus on this question and your exit tickets.